Hello everyone. Continuing with our view of the different stages involved in getting a custom Linux kernel running on a board that we have, right? In this set of videos, we are going to look at the concept of a device tree and how we can describe hardware in such a way that the Linux kernel can identify it and pick it up and make use of it. So, as you might imagine, these are very specific applied problems that we are talking about over here, right? This is in terms of concepts or pure is there some underlying idea behind it that is fundamentally sort of independent of the operating system and so on. That's not really true to a large extent, although you will find that pretty much any operating system needs to solve all of the problems that we are talking about over here, right? The point I am trying to make is that the specifics, for example, of how the device tree operates could have been solved in many other ways as well, right? But we are primarily interested in understanding how we can get embedded Linux, whatever that means, right, working together with a hardware software interface where we basically have some kind of an FPGA type of platform, right? And it turns out that the approach that has been used in embedded Linux, especially on ARM based devices as we have in our Xilinx FPGAs, is to use something called the device tree in order to describe the hardware. So what we are going to do is try and understand why we need a device tree in the first place, how it gets implemented, look at some examples, see how we can modify a device tree for the sort of toy smart timer that we have been working with so far, and finally boot the whole thing up on Renode and show how the device tree helps the system to sort of identify that such a piece of hardware exists. Alright, so broadly the objectives of this set of videos: why do we need a device tree, how does Linux make use of it, right? And what we saw in the previous set of lectures is that we can write a kernel module, which is essentially a sort of device driver. What we mean by a device driver is something which allows us to communicate with the custom hardware that we have. In our case, it was what we called a smart timer, right? And by directly passing in parameters such as the physical base address of the smart timer and perhaps the window size corresponding to the number of registers available for the smart timer, we were able to register it with the kernel. And from that point onwards, we found that there were a few new files that got created, /dev/mmio_demo, /sys/ various other subdirectories and so on, right? And these files are essentially the way that Linux and in general Unix like systems try to make devices available to the end user, right? They try to make everything as far as possible look like a file. The advantage of that, as we already discussed, is that there are already some standard functions in the C standard library to open files, close files, read from files, write to files and so on, which means that pretty much any device, if we can make it look like a file, we can reuse those functions in order to get a much bigger range of functionality than what would be possible if we had to individually go and peek and poke individual registers that are present in the device. So what we have previously seen is that we can pass module parameters while loading the module. What we would like to do now is follow another approach which is called the declarative approach. And the declarative approach essentially says that it's a different style of programming. What we normally do when we write C code is what's called imperative programming. Imperative programming means that we are literally specifying the instructions or the steps that the computer needs to take one after the other. If I say A is equal to A plus B, it's very clear that at that particular point when I reach that step, I want the computer to take the value of A, the value of B, add them together and put the result into whatever was the memory location corresponding to A. Now there is another style of programming that's called declarative programming, where for example we might say that there is a certain thing exists, there is a clock present in the device tree, or there is a serial port present in the device tree, right? It sort of just tells you what are all the different things that are present and how they are connected up with each other, rather than actually saying, okay, take a wire from here and connect it to that, take this thing and then connect it to that clock and so on. In other words, a declarative approach means that the specific order in which you have written down the different parts of what you could call a program, right, may not matter so much. Ultimately, it is possible to sort of infer the overall behavior of the system based on the structure of what is there in the declarative script. It's a little confusing at first. Imperative should hopefully be clear to you. Declarative, I'll try and explain a little bit more as we look at an example of a device tree. But the idea of a declarative approach is that rather than sort of specifying one step after the other to tell you how to load a new driver into the kernel, I can sort of just say this device needs this driver, and the kernel will then figure out how to identify the driver, the device, and connect the two together. Okay, that essentially is what we mean by a declarative approach. So what we will do is that we will author, meaning that we will write, but as you will see, we are not going to write a device tree from scratch, right? What I will do is I will take the existing device tree corresponding to the demo that we showed earlier, modify it in a certain way, and then load that into our emulator Renode, right, and show how that helps us, or rather how it helps the Linux kernel to now identify that we have a particular kind of device present in the system, right. And after doing all of this, right, which is pretty much the way that we have sort of, that we currently use in order to implement the loading of drivers for devices, I am actually going to go take a step back and say, is this the only way that it could have been done? Well, the answer obviously is no, but it turns out that in the past the approach that was followed was actually different, right. There was an approach using what are called custom board files, and not just that, on x86 PCs, your desktop, laptop, any Intel or AMD based system, there is a completely different approach which does not use the device tree, but which uses something else called the ACPI configuration interface, right. So I will briefly mention those, but as far as we are concerned, the main focus is going to be on the device tree, because when we talk about embedded Linux, we are primarily concerned with modern ARM based systems. Of course, as things are going, we might also be interested in RISC-V based systems. They are not sort of common yet, but they are likely to become more common as time goes on. And luckily for us, it turns out that they have also chosen to follow the same device tree based approach as ARM. So whatever we see over here should hopefully be useful for other kinds of processors which you may not have encountered yet also. Okay, so these are the broad objectives of what we are going to look at. Let's get into some of the details. So to motivate the need for a device tree, let me quickly recap what we saw in earlier demos. We basically saw how we can bring up a Zinc-like system in the Renode emulator, right? And we also booted Linux onto it. Now what do I mean by bring up a Zinc-like system? There were two parts to it. I needed to specify the platform, right? And that is in a custom language which is determined by the Renode emulator, right. And we have that REPL scripts that we wrote, where we essentially said there is a CPU, there is a bus, and there are various devices connected onto the bus, right. And then we were able to boot Linux onto it. But you might have noticed that especially in the second demonstration where we booted something corresponding to the Zinc Z board, I mentioned that there is something called the DTB that needs to get loaded in a specific place. Otherwise, the system essentially, well, it boots up. The problem is you don't see any messages as it boots up, right? And that's an important distinction to keep in mind. The system is actually booting, it's working fine. It's just that it doesn't know where the UART is connected, right? And therefore is unable to output messages in such a way that you can actually see them. So the DTP is required not so much for enabling the boot system boot up as such, right? But primarily so that the kernel as it boots can identify the various kinds of hardware peripherals attached to this particular system, and can also decide on where the output messages, for example, need to go, right. So, well, we had a DTB, I didn't explain anything about it at that point, but it booted, right, and it turned out that using that same DTB and without mentioning anything about a smart timer, I could load in a so-called MMIO based device, right, a memory mapped IO based device. What we did was I had a custom module that I wrote, which is sort of a toy module. All that it does is it assumes that there is an underlying storage available where I can write data and then read it back. And in the REPL script, I attached a smart timer MMIO block, and in my kernel module, I essentially loaded it using the irnsmod command by giving it the parameter physical base address is the exact same address as what was used in the REPL script, right. Now, what that means is that I knew the full details of the system. I knew, for example, that my particular smart timer is going to be connected at this particular address, and I passed that information to the module as I was loading it inside the system. Now, this is great for system bring up, right, because I just want to test that I have connected something at a particular address and my software is able to detect it, right. The problem is it is not scalable across boards and instances, right. So, what exactly does that mean? We will take a closer look at that as we move forward.